Welcome back to the next Unit 1 video. In this video we're going to cover the internal coding of numbers, or effectively how we can represent numbers in binary form. Right, so I think currently we've actually looked at positive numbers a couple of times, but this time we're going to look at how we can represent negative numbers in binary. And there's going to be three ways we can do that, right? One is called sign magnitude, the other is 1's complement, and the final one, 2's complement. Now, if you think about today, right, modern devices, I mean, basically all modern devices are going to use 2's complement, right? Whether it's your phone, your laptop, your your desktop, your tablet, right? Even your TV, car, fridge, anything that's got some sort of digital circuit. I mean, basically all of them are going to use 2's complement. Right, then we'll look at the advantages and disadvantages of each, and effectively, why 2's complement is the best, or why this is won out. Right, so this chapter is just going to focus on integers. Chapter 16 in A2 will focus on floating or fixed point numbers. And remember we said floating fixed point, right? I mean, we can also write that as a real, so of course just a decimal number. Right, I think this we've mentioned before, right? Signed and unsigned, and hopefully you remember the signed means it's just going to have a sign, right? Either positive or negative. Whereas if we say unsigned, of course if we say kind of un, right? I mean that just means no. So if we have a number with no sign, basically we're just going to assume that's positive by default. And of course remember in the computer, the computer is not literally storing the sign, +3 or -3. But I mean that's what we're going to see, right? So in this video we'll see how it actually represents this. Right, okay, so traditionally then there's been three different approaches to represent the sign of a number. Again, like we said, sign magnitude, right? 1's complement and 2's complement. And the book mentions all three, although these days, as mentioned, 99.99999 right percent of all devices are going to use 2's complement. And likewise, to be honest, I mean even 99% of exam questions, they're mostly going to focus on 2's complement. Like out of all the past papers I've looked at, I mean probably only I don't know, maybe some of the older papers might have had more sign magnitude 1's complement. But I mean, recently, I don't think, I think they've not actually asked these for a long time, to be honest. Right, so sign magnitude, this is kind of the simplest methods for humans to understand, since basically, I mean, this is just how we write numbers on paper. So here they say, the most significant bit is simply the sign bit, right? If it's 0, it's positive. If it's 1, it's negative. So for example, using 4 bits, and of course, this is value 1, right? This is value 2, this is value 4. Now, rather than saying 8, okay, I guess, we're just going to remove that 8, right? And then, we're just going to make this the sign bit, so, right, either plus or minus. And like we said, 0 is positive, so if we want positive 6, of course, we make this sign bit 0 to mean positive. Then we just go, 4 and 2, right, to make positive 6. Likewise, if we want negative 6, again, we have the 4 and the 2. But in this case, right, we just set the sign bit to 1, because, of course, 1, right, just means negative. So I mean, hopefully that makes sense, right? Hopefully not too complex. And if we just think, what do the words sign and magnitude mean? Because if you understand what these words mean, all right, then the name actually becomes kind of quite logical. So of course, sign is just whether the number is positive or negative, right? Plus sign, minus sign. And magnitude, I mean, basically it's the size of the number, and that's also equivalent to the absolute value. So I mean, if in maths you're familiar with absolute values, I mean, absolute value, just means, positive only. So if we say the absolute value of -5, I mean, basically that's just kind of like removing the 5. Removing the minus. So we're saying, 5, right, is equal to, the absolute value of -5. Since, I mean, basically what magnitude is, just kind of ignoring the sign. And likewise, I mean, if you've done physics, right, talking about vectors, I guess you'd say, each vector is going to have a magnitude and a direction. Like, let's say, I don't know, maybe someone is moving, say 5 meters per second to the right. I guess in physics they generally write it like that, right? And then you could say, right, someone else is moving, 5 meters per second upwards. Well, of course, right, in this case they're going to have the same magnitude, which is both 5, even though their direction is different. Right, so, so this is what's called sign magnitude, since, I guess, right, it works. It works by simply adding a sign in front of the magnitude. And again, I mean, like we can see, so just, +5 or, -5. And, I mean, as mentioned, that's similar to how we actually write numbers on paper. Although, I guess, on paper, we don't actually write the plus, okay, we just Again, we just assume, well, if there's no sign, right, then, well, positive by default. Alright, so if we have a practice at this, so well, let's think, right, we're going to have, what, 1, then 2, then 4, and of course, well, you can keep going if you want, but I think here we're just going to use, well, 1 nibble. So what, to represent 7, well, I guess here, right, so what, there's going to be a 4, there's going to be a 2, there's going to be a 1, that's 7, then of course, what, the sign bit has to be 0, and then if we want negative 7, well, it's just going to be the same, right, so, well, 4, 2, and 1, right, and then of course, just make that negative. Alright, so I think the next two you can try by yourself. Okay, pause the video and then see if you get the answers correct. Alright, so if we look at 79, right, well, 79, well, that's going to be 64, and what, then we want 15. So, yeah, that's what, 64, right, plus 8, that gets us to 72. Right, plus 4 gets 76, right, plus 2, 78, right, plus 1, 79. And again, of course, well, right, 0 means positive, and then, yeah, 1 means, well, minus 79. Then if we think 104, well, 128 is too big. Right, therefore, what, we want 64, and then if we have 64, we have 40 remaining. So we're going to have, what, 64 plus 32. Alright, that's going to get us to 96. Alright, then there won't be a 16, but there will be an 8. So I think, yeah, 64, 32, and 8. Right, that should get us, yeah, to 104. And again, of course, right, just, well, yeah, 0 for positive, and, yeah, 1 for negative. Right, so let's think about the ranges then. So, yeah, well, I guess, yeah, do you remember the biggest number we could represent with 8 bits using an unsigned representation? So again, just pause the video or have a think. So hopefully you might remember that, well, 8 bits, right, the range was going to be from, and again, right, this is if it's unsigned positive only. Okay, so the range was, what, 0, and then, what, 2, 255. And if you remember the formula for that, well, it's going to be 2 to the power, okay, yeah, sorry, right, 2 to the power of n minus 1 like this, where in this case, what, 2 to the power of 8 is 256, therefore 256 minus 1, right, that's 255. Now, of course, if we're talking about signed, so if we were talking about signed, well, this means, right, a negative and positive. Well, in this case, what, the range is going to be, well, minus 128, right, to 127. And the formula for that, well, this one, yeah, let's try not to make a mistake. Right, so this is going to be the smallest value, and let's say 2, and yeah, maybe I can fit it here. Right, that's going to be, what, 2 to the minus 1, minus 1, and in fact, hang on, sorry, okay, yeah, this one should have no minus 1, because, yeah, here we got, what, yeah, okay, yeah, here we have, well, 2 to the power of 7, effectively, right, which is, well, minus 128, right, yeah, when we have this minus in front of it. Right, okay, so, yeah, let's just delete all of that. Alright, so yeah, when dealing with 8-bit unsigned numbers, then how many bits contribute to the magnitude? And if we think about, well, signed magnitude, right, also how many bits will contribute to the magnitude, right, in signed magnitude? So again, right, if you've had to think about that, right, in 8-bit unsigned, then, well, in this case, right, all 8 bits are going to be used for the magnitude. Because of course, what, we have 1 here, and then, yeah, well, 1, 2, 4, 8, 16, 32, 64, right, up until 128. So of course, right, all of these bits, right, they're all going to contribute to the magnitude. But if you think about signed magnitude, well, 7 bits will be used for the magnitude, since we say, what, well, I guess, let's say the most significant bit, right, the most significant, right, or the leftmost bit is going to be used for the sign. So probably you can see that, I mean, yeah, this means, well, the range is going to be slightly less, although in reality, since we're also representing negative numbers, yeah, it's actually only going to be 1 less. Right, so let's think then, what would be the biggest and smallest meaning, well, most negative in this case, right, since it's signed magnitude, yeah, that we can represent using 8 bits, or yeah, 8-bit signed magnitude. So I think here, well, you just want to think about the bit pattern. Now, the biggest number, well, of course, right, we want the first bit to be 0, okay, since we want it to be positive. Then, of course, well, we're just going to want all the remaining bits to 1. Okay, right, hang on, yeah, okay, that should be, yeah, okay, right, yeah, it's kind of here, right, so yeah, 4 bits, 4 bits. Right, so here then we've got, of course, well, the first bit is 0, right, then the next 7 bits are all 1s. And if you add those up, well, that's going to be 127. Now, if we want to make the smallest, well, I mean, these 7 bits are going to be the same, but then we just have, what, the first bit is going to be 1. So, yeah, I guess in this case, what, just 8 1s? Yeah, okay, that's 8. And of course, well, this is going to equal, what, minus 127. So yeah, we can see that here, all right, the biggest and smallest. So let's think, well, what would be a formula to represent the biggest and smallest number using n bits for sign magnitude? So for this one, I guess you want to think, well, if we're using 8 bits, remember 2 to the power of 8 is going to be 256. So what you want to say is, well, only 7 bits are going to be representing the magnitude, right? Therefore, well, it's going to be 2 to the n minus 1. But then we also want, well, both, positive or negative. And I guess we also have to minus 1 as well, because yeah, otherwise it would be what, 128. But yeah, we're only representing, well, 127. So I think, we can basically just have this, all right, and then we'll just go, yeah, plus or, I guess, let's see what, plus or minus. Yeah, okay, so yeah, just like that. Right, so I guess while it might seem like sign magnitude just works, there's actually a problem that, well, sign magnitude is not going to work well for arithmetic, because let's try the calculation, well, 5 plus negative 5. Now, of course, this should just be 0, and we're in binary, what, 0, 0, 0, if we're just using 4 bits, for example, or yeah, using, a nibble. Now, this one, well, this is going to require binary addition, and, well, currently we've not looked at binary addition, or I think that's going to be the next video. But if we just go over how to do it quickly. So here, well, 1 plus 1 in binary, right, that's going to be 0, right, but then we carry a 1. Right, then if we have here, right, well, 1 plus 0 plus 0, well, here it's just going to be 1 because, well, yeah, right, 1 plus 0 plus 0. Yeah, right, like, basically there's no carry. Right, then if we go to the next one, so here, well, 1 plus 1, right, again, that's going to be 0, okay, but then there's a carry of 1. And then here, well, 1 plus 0 plus 1, again, that's going to be 0, right? But then, well, in this case, there's going to be something called overflow. And yeah, I guess, basically, we're just going to ignore that overflow. Now, don't worry if you don't understand that, because, well, we're going to cover this in the next video. But, if you think, well, it's the same as what we do in denary, right? Let's imagine we have, I don't know, 75, and then you add 18. Well, if we add that, right, 5 plus 8, well, that's going to equal 3, right? And then we're going to carry the 1. Then, of course, here, well, 1 plus 7 plus 1, that's going to be 9. So that's kind of what we're doing here, right, where we say, well, 1 plus 1, right, it's going to equal 0, okay, but then, well, then we carry the 1. And the reason that works is because, okay, well, let's just do this in denary. So 1 plus 1 in denary, well, that's going to equal 2. Now, if we think in binary, well, 1 plus 1 in binary, okay, that's going to equal 1, 0, okay, because, of course, well, 1, 0 means 2. So what we're thinking is, well, yeah, here, right, this is where the 1 comes in, right, this is the 0. So, of course, well, yeah, we say, right, this 1, right, well, that's just, right, this carry 1 here. And then, of course, well, yeah, the 0, well, that's just, this 0 here. Yeah, so hopefully that makes sense. Although again, right, don't worry if it doesn't. All right, but if we look at this then, well, we see this answer is not actually 0, okay, because, well, here we've got, well, yeah, 0 for the sign, so it's positive. But then, right, in the magnitude, we've actually got 2. Okay, so basically the key point is that, well, sign magnitude, the arithmetic is not going to work. Or I guess it's not going to work kind of directly. So, right, let's think then, what do the numbers, well, 0 and, yeah, I guess, well, 1, 0, 0, 0 represent? So if you think about the magnitude, well, here the magnitude is 0, right, and then the sign is 0, so basically positive 0. Right here we have what the magnitude is 0, okay, but then the sign is negative. So what we've got is, well, basically we've got 2 representations of 0, and, again, right, positive 0, minus 0, or negative 0. Now, of course, well, one that's going to be wasteful, right, is just, yeah, using this bit pattern, whereas, of course, yeah, that bit pattern could be used for something else. Yeah, and it's also quite strange that there's going to be 2 representations of 0. So this is actually one of the reasons that causes the arithmetic not, yeah, I guess not to work that well, right, with sign magnitude. Technically it is possible to design circuitry to correctly perform, sign magnitude arithmetic. But because of these weird, edge cases, right, because of this weird, having 2 values of 0, you can also get another thing where, let's say if you have like a positive number plus a positive number, so I don't know, maybe just like, 1 plus 1, or in fact, I don't know, like, okay, let's say we have something like this, right, 1 plus 1 plus 1, and say, right, these are 2 positives. Well, right, then this 1 is going to go here, because of course, well, 1 plus 1 plus 1, right, that's going to have an answer of 1, right, then also a carry of 1. So in this case, well, then when we do this, right, 1 plus 0 plus 0, this is now going to become 1. So effectively what's happened is, well, our two positive numbers that we've added, right, they've now got a negative sign. So yeah, again, I mean, like technically it is possible to design circuitry to, you know, perform, right, sign magnitude arithmetic, but because there's two representations of zero, right, because we also have these kind of weird edge cases, yeah, then the circuitry, well, it's going to be complex, it's going to be inefficient, right, and also more expensive because, well, basically we just need, yeah, sort of more logic gates, right, in order to, you know, correctly perform this. Yeah, so well, that's why in a minute, right, eventually we'll see that we're going to use something called 2's complement. Right, so if we look at the next one, well, 1's complement, so yeah, well, right, we saw sign magnitude had two issues. Right, another approach developed was, well, yeah, I guess called 1's complement, and right, yeah, that was developed to try and solve these issues. Now, 1's complement, right, this is also quite simple, and it just means, well, flipping, right, also called, yeah, inverting or negating the bits to convert from positive to negative and vice versa. So if we say 5, well, and of course, well, this is going to be 1, this is 2, right, this is 4, this is 8. So yeah, of course, well, this is just 5, right, hopefully, yeah, people know this. Then if we want to convert to negative 5, well, then we're just going to flip the bits. So when we say flip, well, that means, right, if we see a 0, right, then a 0 becomes 1. If we see a 1, right, well, then, yeah, then a 1 becomes 0. So we see that here, right, where we see, well, this 1 becomes a 0, right, this 0 becomes a 1, yeah, this 1 becomes 0, right, this 0 becomes a 1. So, I mean, again, I mean, here you say, well, we flipped the bits, right, we inverted the bits, or we negated the bits. Yeah, all of those, right, all of those terms are equivalent. Right, and then here, so note that we actually don't need a sign bit, and here all bits are going to contribute to the magnitude. So again, I mean, yeah, while it might seem that 1's complement solves the problem, we're going to have the same problem where if we try, let's say, 5 plus negative 5, right, again, of course, this should equal 0, or yeah, should equal, you know, 4 zeros like this. But if we look at that, right, if we do the same addition, well, 1 plus 0, right, that's going to be 1, 0 plus 1, that's 1, right, 1 plus 0 is 1, and, well, 0 plus 1, right, that's also 1. So here, well, the expected answer, of course, is 0. Right now here, I mean, yeah, I guess for 1's, right, it seems like a strange answer, although in 1's complement, right, this is technically not actually wrong, right, yeah, yeah, I guess for this particular sum. And we'll see this here because, well, let's think again, how can we represent 0 in 1's complement? Now, of course, well, the easy way is what, just 4 zeros, okay, if we're using a nibble. But let's think, I mean, this is kind of like positive 0. Now, remember that if we invert the bits, right, or if we, yeah, negate the bits, so what, that's going to become 1's like this. Well, effectively now, this is kind of like negative 0, right? So again, we've got the same problem where we've got, you know, two representations of 0. And again, right, so of course, well, this is both redundant, right, and it's also a reason why the arithmetic doesn't work. Right, so if you try some more additions in 1's complement, then you'll notice the answer is always 1 less than what it should be. So, for example, if we do, right, 9 plus negative 3, right, so of course, well, effectively just, yeah, right, well, 9 minus 3. But I mean, well, so far we've not looked, yeah, I guess, well, we've not looked at subtraction yet, right, so that's why I'm saying 9 plus negative 3. Right, then in 1's complement, this would equal 5, right, whereas, of course, the correct answer should be 6. And I suppose, yeah, if you want to do this again, well, of course, right, 1 plus 0, yeah, okay, is it going to tell us? Yeah, okay, alright, so 1 plus 0 is just going to be 1, right, well, 0 plus 0 plus 0, right, that, okay, sorry, yeah, 0 plus 0 is 0, right, 0 plus 1, alright, that's going to be 1, and then, well, 1 plus 1, alright, that's going to be 0, of course, well, remember the carry 1, but we see, well, this will be overflow, and as we'll see in a future lesson, right, overflow we just ignore, yeah, since we don't have that number of bits. Right, so if we just kind of sum up everything I've said, we said that 1's complement will result in an error of -1 for arithmetic. So, I mean, well, yeah, I guess when I said -1, yeah, we say what the answer it gives is going to be 1 less than the answer it should be. So, yeah, we get kind of an offset of -1, effectively. Right, then let's have a practice then. So if we want 3, and again, right here, we're just going to use 4 bits. So let's go, what, 1, 2, yeah, 4, and 8. Now, of course, well, to represent 3, well, we're just going to have a 1 here, a 1 here. And, of course, well, yeah, 0 for these. Now, of course, -3, well, then we're just going to invert the bits, right? So, well, 1, 1, right, 0, 0. Now, again, pause the video, right, have a go at the other two, see if you can do those yourself. Okay, so if you've had a go at those, well, 26, well, that's going to be 16, right, then it's going to be an 8, right, that gets us to 24, right, then, of course, just a 2, and again, yeah, well then just flip the bits. Right then 107, so what, that's going to be 64 plus 32, right, that gets us to 96. Then if we go plus 8, that's 104, and then what, plus 2 gets us 106, and then plus 1, 107. And again, of course, we'll take that, right, then just invert the bits, yeah, to get minus 107. Right then, if you look at 2's complement, so right, that's going to be, yeah, this final column. Right, we see the negative values are plus 1 compared to the 1's complement. Right, there's also only going to be 1, 0, right, and we also get this extra value of negative 8. And I think here we can see this. So we say, right, of course, well, right, this 1's complement value, well, this just moves down into this position. Of course, yeah, this 1's complement value, right, moves down into this position, yeah, of course, etc. And the reason for that is because, well, here we don't have, yeah, I mean, well, yeah, basically, right, we don't have this negative 0. So because we don't have this negative 0, well, you know, that's why it gets pushed down, yeah, to the next value, which of course, well, in this case is, well, minus 1. So because they get pushed down, well, that also means we get the advantage of having this minus 8 as well. So we see 2's complement, right, there's, well, 2 advantages, right, 1, okay, we only have 1 representation of 0, right, 2, okay, we also get this extra value. Right, so as mentioned, well, 2's complement, this is what's actually used in, well, yeah, 99 point, I mean, like, basically 100%, really. Yeah, I mean, you're probably really going to struggle to find something that doesn't use 2's complement. Right, so this approach works by making the most significant bit negative. For example, with 4 bits, right, 5 and minus 5 would be represented as follows. So here we see, well, yeah, we see what the most significant bit, right, or the leftmost value is going to become negative. So to represent 5, well, of course, right, that's just 4, yeah, 4 plus 1, right, that's 5. But then if we want to represent negative, then what, a negative, that means that the first bit always has to be a 1. So here we have, what, negative 8, and then we want to think, well, what do we want to plus to negative 8, right, to get us back to minus 5? So of course, well, in this case, if we go plus 2, right, that gets us to negative 6, plus 1, right, that gets us to negative 5. And yeah, I guess you can see all those sums there. Right, so yeah, let's try again then. So we're going to do a 5 plus negative 5, right, this time using 2's complement. So in this case, well, right, we have 1 plus 1, right, that's going to be 0, okay, but then carry the 1. Right, then we have, well, 1 plus 0 plus 0, right, so here we have 2 1s, therefore, again, what, the sum is going to be 0, okay, carry the 1. Here, well, 1 plus 1, okay, yeah, sorry, 1 plus 1 plus 0, again, 2 1s, right, therefore, well, sum is 0, right, carry the 1. And then here again, well, 2 1s, right, 1 plus 0 plus 1, right, sum is 0, carry the 1. And again, of course, right, this is going to result in overflow, but yeah, as mentioned, right, we just ignore that overflow. Then in this case, of course, well, you can see this is working, because here, well, 5 plus negative 5, right, yeah, that's just going to equal 0, right, as we can see here. So of course, well, because the arithmetic works, right, this is what, well, I mean, computers or, yeah, phones, right, just electronic devices actually use. So let's look at a more difficult example. Right, suppose we want to represent minus 120, okay, sorry, minus 102 in 2's complement. What would the value of the most significant bit be, and how many bits would we need? So if you think, well, let's say, what, I mean, minus 64, that's not going to be big enough, because of course, well, yeah, we need minus 102. But then if we go, well, minus 256, right, that's going to be too big. So I think, well, I mean, yeah, of course, well, the one we can use, right, minus 128. And I mean, actually, minus 256 will work, which we'll see in a minute, because, well, I mean, basically, well, leading 1s in 2's complement is going to be fine. Well, yeah, that's not going to sort of affect the negative value. But I think here, well, let's go minus 128, and then we want to think, well, so of course, right, this is going to be a 1, because, well, of course, yeah, we need to make it negative. Right, and then we need to think, well, what do we need to add to minus 128, right, to get us back to, right, minus 102? So, I mean, hopefully you can tell, well, of course, we need to add 26. Yeah, okay, we need to add 26 to minus 128, right, to get us the minus 102. So let's just write all of these out. Well, so 64, right, 32, 16, yeah, 8, 4, 2, and 1. So to get 26, well, there's not going to be a 32, right, there. Okay, sorry, yeah, there won't be a 64, there won't be a 32. Right, there will be a 16. Okay, there's also going to be an 8. That gets us to, what, 24. Right, there won't be a 4, right, there will be a 2, and then there won't be a 1. And now if you want, you can check this. So what, minus 128, right, then if we plus 16, so what, that's going to become minus 112. right, then plus 8, well that gets us to what, minus 104, right, plus 2, yeah, that gets us to what, minus 102. Yeah, and again, I mean, this is kind of just what we said. Right, so in this case, yeah, n would be 26, right, therefore the other 7 bits have to add up to 26. And yeah, this is just showing that. Let's just have some practice then. So we see the first one, minus 7. Well, of course, right, that means we are going to want this minus 8. Right, then, of course, well, to get from minus 8 to minus 7, we just want to add 1. Right, so there's not going to be a 4, there's not going to be a 2, right, but there will be a 1. Because, again, what that's doing, well, right, minus 8 plus 1, right, that's equal to minus 7. Now, these next ones, I would say pause the video, have a go yourself, and then, yeah, check and, right, yeah, see if you get the correct answer. Alright, so if you've had a go, well, let's look at this one then, right, again, well, minus 35, right, therefore, of course, well, this has to be, yeah, this has to be minus 128. Right, then if we go, well, plus 64, okay, this is going to get us to minus 64. Right, then if we go plus 32, well, that'll get us to minus 32. So in that case, well, that's going to be, what, too big. So yeah, okay, we're not going to have that. Right, then if we go plus 16, that's going to get us to minus 48. Right, plus 8 gets us to minus 40, plus 4, minus 36. Right, there won't be a 2, and then, yeah, there will be a 1. Right, that gets us to minus 35. And yeah, let's just check those. Yeah, okay. Right, then if we look at the final one, so I think here, I mean, I'm going to think, well, what do I need to add to minus 128 to get to 76? Right, and what that's going to be 52. So here, what there's going to be minus 128, and then, yeah, from these, what, remaining 7 bits, then I want to make 52. So, of course, well, there's not going to be a 64, right, but there will be a 32, and what, then we just need to make 20. So what, there will be a 16, there won't be an 8, right, there will be a 4, and then, yeah, no 2 and no 1. And yeah, okay, right, so they're fine. Right, now let's look then, how can we convert from positive to negative? Then, and I guess, yeah, if we want to convert from, let's say, 12, right, to its negative equivalent, right, i.e. minus 12, then there's this simple method, right, well, just flip the bits, okay, then we add 1. And yeah, hopefully you can remember that rule. Right, so if we think back to 1's complement, then maybe you can figure out why we need to add 1 to get the correct answer in 2's complement. And the reason for that, well, yeah, let's just go back a bit. Right, so if yeah, if we go here, remember that we said, well, in 1's complement, right, if we add 1 to this, right, then it's going to go, you know, to the correct value here in 2's complement. So yeah, okay, right, add 1. Right, yeah, I mean, of course, right, that's why that's working. Yeah, and right, of course, well, yeah, the reason is because what arithmetic answers in 1's complement were always off by minus 1, right, therefore if we add minus 1 to the answer, then the answer will be correct. Right, so if we want to try converting from, well, 12 to minus 12, then how many bits do we need? So I guess you can think, what, to represent 12, now if we only have 4 bits, that's not going to be enough, because, well, I mean, let's think, right, so, well, 1, 2, right, 4, right, 8, but the thing is, right, if we've only got 4 bits, well, then the most significant bit is going to become negative. So, of course, well, with this, you know, what the biggest number we can represent would be 7, the smallest number we could represent would be minus 8, right, so therefore what we actually need, well, we need to go to 16, and yeah, we're going to make the 16 negative, right, since well, here we're just using 5 bits. Right, so to represent 12, well, of course, right, there's not going to be the minus, right, but then there will be the 8, there will be the 4, right, so yeah, that's going to be, right, that's going to be 12. So if we think then this method of, well, flip the bits, then add 1. So, well, flipping or inverting the bits, well, we see here, right, 0 becomes 1, right, 1 becomes 0, yeah, 1 becomes 0, and then, well, yeah, these zeros, they become 1s. Right, then if we just add 1, and, I mean, like, yeah, maybe just kind of ignore this, right, because, well, and, well, let's just write this here. Right, so, well, I mean, this is going to be, well, let's just call it x, right, it doesn't really matter what this is. I mean, technically, it's the 1's complement, right, of this one. And then, well, here, this is just going to be 1, right, and, well, then we're just going to plus those to, okay, yeah, sorry, 1. Right, then if we just plus those together. So here, well, right, 1 plus 1, well, again, that's going to be 0, carry the 1. Right, 1 plus 1, well, again, 0, yeah, 0, they carry the 1. Right, 1 plus 0, right, that's 1. 0 plus 0, yeah, that's going to be 0, and then, well, 1 plus 0, right, that's going to be 1. And here, let's just check this. So, I mean, right, this should be our answer of minus 12. And if we check that, well, here then we've got, what, minus 16. Yeah, that's this one. Right, then we've just got 4. So of course, well, that's going to be correct, right? Minus 16 plus 4, yeah, that's going to be equal to minus 12. And then I think, yeah, I mean, maybe I can just erase that. But this here is going to be shown, I mean, basically what I've just done. So yeah, I mean, you can, have a look through that again, right, if it doesn't make sense. Right, okay, so yeah, let's think then, well, if we're using 5 bits, then, well, 12 is going to be this one. So yeah, this is what 8 plus 4, right, of course, well, this is going to be 16 plus 4, right, to make negative 12. However, what would these numbers be if we used 8 bits? So, I mean, you can think, well, for the positive 12, it's just going to be this, right? Because, of course, right, there's not going to be the 128, there's not going to be 64, right? No 32s, no 16s. But yeah, we will have the 8, we will have the 4. So effectively what we're going to get, well, we're just going to get these kind of leading zeros here. Yeah, and of course, well, this kind of sign, the negative one is also 0, right, since it's positive. Likewise, we see that, well, we also get these leading ones here, right, on the negative. And something we can say is, well, the leading zeros for a positive number are redundant. And I mean, if you think about this in denary, right? Let's say we have 3 in denary. Well, that's also equal to just something like this, right? Because of course, yeah, these leading zeros, right? They're just redundant. They have no effect. Right, but then if we look at negative numbers, well, let's check the leading ones for the negative value. So if we think here, well, right, we say, yeah, this was our representation of minus 12, right, if we're doing it in 8 bits. Whereas, yeah, this was our representation of minus 12 here, right, if we're using 5 bits. And we'll see that this actually works because, well, the first one is minus 128, right, plus 64 gets us to a minus 64, right, plus 32, this gets us to minus 32, right, plus 16, well, that's going to get us to minus 16, and then, yeah, plus 4, right, that's going to get us to minus 12. So what we can say is, well, in this case, what we've added these 3 extra ones, right, just to make it up to 8 bits. And yeah, I mean, these 3 extra ones, right, they're going to have no effect. Since basically, like, if we have, the negative number, and then, yeah, because if you notice, right, when we do minus 128 plus 64, right, that just becomes minus 64, our kind of running total for these two. And of course, like, that's just equivalent to, well, yeah, I mean, that's just equivalent to, kind of not having this one. And of course, let's say if we only have 7 bits, because of course if we only have 7 bits, then this first one would be negative. And yeah, we said, well, of course, minus 128 plus 64, right, that's also going to be minus 64. Yeah, I'm not sure if that explanation makes sense, but the key thing to notice again is that, well, if we have leading ones in a negative number, right, then, I mean, basically they're just redundant, right, it's kind of equivalent to leading zeros in a positive number. Right, okay, yeah, okay, so, well, that's just going to recap. Yeah, so let's skip that, right, just says the same thing. Right, so let's get some practice then. Using the flip the bits and add 1 method, convert the positive numbers to negative, and answers should use 1 byte. So we want to convert, well, 17 to minus 17, 48 to minus 48, and 90 to minus 90. So I think, right, I'll just try this one, and again, right, the other two you can do yourself. So 17, well, first we want to write the positive representation, and right, it says 1 byte. So if we need to, well, let's go 100, and I suppose, yeah, let's make this negative. Although, yeah, for the positive version, right, it doesn't really matter. Right, then, well, 64, right, 32, right, 16, 8, 4, right, 2, and 1. So, of course, well, there's going to be, yeah, no minus 120, right, no 64, no 32, right, there will be a 16. And then, of course, right, there's going to be a 1 as well. Right, then we flip the bits, so, well, 0 becomes 1, and then, yeah, 1 becomes 0. Right, then we just want to add 1 to this, and actually this one is going to be really easy, right, since this is a 0, then if we add 1 to this, and, well, yeah, let's just do this here, right, so that this is going to be our 1. Right, okay, yeah, I guess, if we do, right, this number, yeah, let's say these two, so if we do, yeah, this number 1, right, added to this number 2, well, basically, right, this 0 is just going to change to a 1, right, because, well, of course, we're adding this one. So our final answer is just going to be this then. And again, of course, well, you can check your answer just by adding them up again, making sure that this is equal to minus 17. But one way you can actually check this quickly, right, just looking at this specific example, is that, well, if we have all 1s, so, and of course, this doesn't matter how many we have, right, I mean, even this is the same, right, this is always going to be equal to minus 1. So here you see, well, we don't have the minus 16, right? Therefore, if we have, well, -1, and, you know, we also don't, okay, sorry, yeah, we also don't have the +16, right? Well, of course, therefore, that's going to be -17, right? Since, yeah, since we're not adding 16 to it effectively. And then, yeah, well, again, let's just erase this, but I think if you do that, well, you should get that one, and then, well, 40, yeah, -48, right, you should get this, and, right, -90, okay, you should get this. And again, of course, you can easily check this because, well, here, right, this is what, -128, and then, yeah, well, of course, well, that's going to be, what, 32, right, and then that's going to be, what, 4 and 2, and, yeah, if you add all those up. Right, okay, so let's think then, well, will the flip the bits and add 1 method also work from negative to positive? Yeah, just have a think. Now, probably a common attitude, or yeah, a common sort of theory you might have is, well, rather than maybe saying add 1, you know, maybe you just have like subtract 1. And to be honest, you know, that's what I would also think as well. But if we actually try this, okay, I mean, we'll actually see that this works, yeah, just by using the add 1. So let's say we have, well, 6, yeah, okay, so let's convert 6 to -6, right, then convert -6, right, back to 6. And for this one, let's only use 4 bits. Right, so I'm just going to do it here. So, right, 6 then, well, let's go, right, -8, right, 4, 2 and 1. So, of course, well, 6 is just going to be, what, a 4 and a 2. And let's go 0 for the -8. Right, using the flip the bits and add 1. So, of course, well, flipping them, right, it's going to become this, right, add 1. Well, yeah, let's just write out the 1 here. Right, so adding the 1, well, 1 plus 1, right, that's 0, right, but then carry the 1, 1 plus 0, that's 1, right, 0 plus 0, and yeah, 1 plus 0, right, that's 1. And I would say, you know, always check this. So here we've got, what, -8, right, plus 2. So we see, yeah, that, I mean, that correctly equals -6. Right, so now then let's take this -6. And then here what, so of course, right, this is our answer. Well, now we want to flip the bits and add 1, right, to try to get back to 6. So if we flip the bits here, well, that's going to become 0, that's a 1, that's a 0, that's a 1. Right, then if we add 1, so, well, let's write the 1 again. Yeah, okay, right. Yeah, I was seeing if it was the same. Alright, okay, well then here then if we go, well, 1 plus 1, right, that's going to be 0, okay, but carry the 1. Right, and then here, well, 1 plus 0, right, that's going to be 1. 1 plus 0, right, that's 1. And then, yeah, 0 plus 0, right, that's going to be 0. And of course, if you just add those up, what, 4 and 2, right, that's going to be 6. So, yeah, I mean, that's something that's kind of useful to know, right, that, right, this method, you know, flip the bits, add 1, it works from positive to negative, right, but likewise, it also works from negative to positive. Right, okay, well, so far then we've looked at 2 methods to calculate the binary representation of a, right, negative ternary number in 2's complement. So, well, either we can do it directly where, you know, the most significant bit is negative, the rest are positive, and just kind of add them up. So again, if we want like -5 and we're using 4 bits, well, of course we say, well, -8, right, 4, 2, 1, right, therefore -5, well, there's going to be a -8, right, there won't be a 4, yeah, there will be a 2, then there will be a 1. So when I say do it directly, again, you just sort of calculate it in your head, right, just, yeah, you know, just write this one down as the negative, and then think, right, what do you need to add to that, right, to sort of get the correct value. Right, the other method, well, as we've seen, that's just going to be, what, flip the bits, add 1. So honestly, like in the exam, I mean, you can use both of these, although the thing is, in the exam, it will say show you're working. So whichever method you use, again, right, make sure to show you're working. And to be honest, I mean, it's good to be familiar with both because, like, sometimes they might have, I don't know, maybe like, well, I mean, okay, so, all right, let's say in one of the later chapters, there'll be something called a trace table. And basically that's kind of like working through an algorithm, okay, but by hand. And sometimes they might have, for example, this algorithm, but, you know, in the trace table. So yeah, that's why it's good to be familiar, you know, again, with like both of these approaches. Right, there's also going to be one other method you can use, and again, likewise, sometimes this has been given as a programming task in the exam, where they won't actually expect you to sort of program it by yourself. But for example, I don't know, maybe they'll give you the code, and again, they'll want you to walk through on paper, or yeah, they'll want you to, I don't know, you know, type it up in code or something. And to be honest, well, if we're talking about, you know, sort of converting it to, yeah, real code, well, that's going to be an A2, since AS, well, that's only pseudocode anyway. Right, so this one, and this one's actually going to be super quick, right? So we start from the right, then we go left, or yeah, start from the least significant bit, all right, then go left. We're going to keep all the bits the same until and including the first one that we see. right, then after the first one, we're going to flip all the remaining bits. So yeah, okay, well, I mean, here you see what this, I mean, basically only 2 stages, because, I mean, yeah, this is just telling us where to start. And this is actually doing the same as the flip the bits and add one method, but it's just going to do it more directly. So if, for example, we see this, well, 0, 1, 1, 0, then, well, let's look at the rule. So again, okay, so right, obviously here we're starting from the right, then we're going left. We're going to keep all the bits the same, and, well, yeah, until and including the first one that we see. So because this is a 0, well, then it just stays the same. Right, the next one, well, this is going to be the first one that we see, right, therefore we keep it the same, right, because, yeah, that's this rule, yeah, up to and including the first one you see. Right, okay, well, now, of course, we've seen the one, so here, right, after the first one, then flip all the remaining bits. So here we say, right, okay, well, this one, so this 1 becomes 0, right, this 0 becomes a 1. And again, of course, you can check that, well, that's going to be -8 plus 2, right, that's going to be -6. So yeah, I mean, that's super simple. And, well, let me just erase this. Yeah, so just to kind of hammer home the point that, well, this one, right, we're keeping the same. All right, this underlined one here, right, this is the first one we see. And then, of course, well, these on the left, right, these are the bits that we're flipping. So I think, yeah, of course, well, I mean, this is going to be extremely quick. And again, this also works from positive to negative, negative to positive. And I would say this is a method you can use to check your answer if you want. I wouldn't really recommend doing this in the exam because, again, the exam says show you're working, and with this it's kind of difficult really to show any working. But I mean, if you just want to have a practice of these, and yeah, you'll see how quick it is. Right, so this first one, well, here then we see the first one, right, therefore this stays the same. But since we've seen the first one, well, all of these remaining ones are going to flip. Right, then if we try the next one, so again, actually, right, this is the first one, so this stays the same. Right, and then, well, all of these others. Okay, yeah, I think I counted that correctly. Right, all of those others, they're going to flip. Right, if we look at this one, well, so here we've got, yeah, 0. Right, so 5 zeros. Right, then we see the first one. All right, then these next two, of course, they're going to flip. And then, of course, well, yeah, I mean, likewise, right, what these ones are going to stay the same. And then here, well, right, this one is going to be a 0, and yeah, these are going to change to 1s. Alright, so yeah, hopefully that makes sense. Okay, then I think just to sort of finalise, because yeah, some people do get confused with 2's complement. Right, some people, when they see, you know, I mean, maybe a question says, right, sort of write the number, yeah, let's say here, right, okay, write 37 in 2's complement form. Then some people, they think, well, because they've seen 2's complement, right, that means they always have to flip the bits and add 1. But the only time you have to do this flip the bits and add 1 is if, for example, you want to convert from 37, right, and let's say, what, converting that to -37. So if you just want to write the positive number, well, then, of course, you just write the positive number. And yeah, I mean, that's going to be this, right, because, again, what, -128, right, then, of course, well, 64, 32, 16, right, etc. And, of course, what, 37, that's going to be, well, 32 plus 4 plus 1, yeah, which is what we're going to see here. So yeah, if it says, well, write in 2's complement form, right, of course, well, that can be positive or negative. And of course, well, it's negative if it starts with a 1. Yeah, obviously, if it starts with a 0, it's going to be positive. Right, then it might also say, well, write 37 as binary or signed binary number. And actually, this is just saying the same as 2's complement. Because, I mean, when we say signed, well, of course, right, this means positive or negative. And basically, I mean, well, since 2's complement is the default, then yeah, when they just say, you know, write it in binary or write it in signed binary, I mean, well, what they're saying is, yeah, just write it in 2's complement. Since, again, I mean, this is what, you know, computers, right, phones, tablets, right, I mean, yeah, that's what they all used. Of course, if they want you to write in, well, yeah, let's say 1's complement or signed magnitude, well, then, of course, they would say, you know, write 37, right, in 1's complement, or write 37 in signed magnitude. Right, if in contrast they say, well, write in unsigned binary, then remember, unsigned means, well, only positive. So let's say if they say, I don't know, maybe use 4 bits to represent, let's say, 12. Well, then, of course, 4 bits to represent 12, what we're going to have, well, 8, 4, 2, and 1. And notice, of course, well, since it's unsigned, right, yeah, okay, we're not using -8, right, we're using +8, all right, since it's unsigned. Right, therefore, of course, well, to represent 12, that's going to be this. Right, so that's why, of course, you need to know the difference, that if it's unsigned, well, this is going to be 12. However, if we were using signed, well, then this same bit pattern, what is going to be -4, because, of course, yeah, using signed, it's going to be -8. Anyway, guys, I think, yeah, I mean, in that video, well, that's all I wanted to cover. It's gone on quite a long time. But hopefully this video was useful, and as always, if you have any questions, just ask in the comments, and hopefully see you again in the next video.